For our final example of how to bound summations and determine their complexity, we're going to look at an increasing geometric sum. This is increasing because the number being raised to the I is bigger than 1, and therefore as you plug in bigger and bigger values of I, it gets bigger. This summation, if we write out the terms, is n times 3 to the 0 plus 3 times n plus 9 times n plus so on. Each term is getting subsequently bigger, so it's an increasing sum. It turns out our bounding technique critically relied on the fact that r was less than 1 because we use the infinite geometric series formula. So we cannot bound this. In general, when you have an increasing geometric sum, you have to use the formula for a finite geometric sum. There's really no way around it. So we cannot, unfortunately, use our technique we did for bounding. We have to use the formula here. So T of n is equal to, I'm going to factor the n out of the summation because it does not have an I inside of it, and write this as the sum from 0 to log base 3 of n squared of 3 to the I. We're again going to use the exact same formula we did in our previous problem. So this is equal to n times quantity 1 minus r to the n plus 1. R in this case is 3. Our n, which is the top bound of the summation in the formula, is log base 3 of n squared. So we have the top bound of the sum, log base 3 of n squared, plus 1, divided by 1 minus r. And now we simply have the algebra problem of simplifying, and then we might need to bound it in the end to get it equal to exactly what we want. So this equals, the denominator here is 1 minus 3, which is negative 2. So this is negative n over 2 times quantity, 1 minus, I'm going to rewrite the 3 to the log 3 of n squared plus 1 as 3 to the log 3 of n squared times 3. This is equal to negative n divided by 2 times 1 minus, I can rewrite 3 to the log 3 of something as the something, because 3 and log base 3 in terms of exponentiation and logs are inverse functions of each other. Let's now distribute the negative n over 2. This is equal to negative n over 2 plus n cubed times 3 divided by 2. I don't like the leading term being negative, so I'm going to rewrite this as 3n cubed divided by 2 minus n divided by 2. I now need to bound this above by a number times n cubed and below by a number times n cubed because we identified that looks like n cubed. So I need to bound this above. When bounding above, you can always drop negative terms. So it's just less than or equal to 3n cubed divided by 2. And to bound below, you can bound below by replacing negative n over 2 with negative n cubed over 2. So off to the side before we do that, let's find out when is that justified. Negative n over 2 greater than or equal to negative n cubed over 2. Cross multiply by negative 2 and you get n less than or equal to n cubed, which is 1 less than or equal to n squared, which is 1 greater than or equal to n. Remember, we're ignoring the negative value because n is assumed to be a positive integer or at least a natural number. So we can make this replacement so long as n is greater than or equal to 1. So we replace negative n with negative n cubed over 2. This is then combined to be a nice 3n cubed over 2 minus n cubed over 2 is 2n cubed over 2, or just n cubed. So it is bounded above by a constant times n cubed and bounded below by a constant times n cubed so long as n is sufficiently big. In this case, sufficiently big meaning n greater than or equal to 1. Therefore, it is in theta of n cubed. Let's write out y. Thus, t of n is in big O of n cubed and big omega of n cubed. And therefore, it is in theta of n cubed. T of n is in theta of n cubed. And notice the technique we did here was very similar to what we did for the decreasing geometric sum, which is why some people prefer to use the formula. I do not care what technique you use. Both of them are equally valid. However, again, I prefer bounding a decreasing geometric sum with the series because it makes the algebra a little bit nicer. This can get messier as the constants become messier. This problem may be not so bad. Others could be much, much worse. So, if you have an increasing geometric sum, you effectively have to use the formulas. and there's no way around it. There are ways around it, but for now, we'll just leave that as that's what you have to do. It's typically easiest just to have one approach and not sort of have too many options for attacking a single problem.